Jordan, welcome to the show. Where do you see the data ecosystem in the next 5 years?
Yeah, thank you for having me. I think there are a few kind of trends that are starting to proliferate now, maybe have over the last couple of years, and I think we're going to continue to see those moving in the same direction, and then, maybe even some more. So I think number one that I see pretty constantly throughout the ecosystem is just to stop processing anything unless it's in a column batch. And I think this actually applies to both batch and streaming processes. So, for years, kind of a lot of the batch processing workloads that we did were dominated by something like Spark. And now all of a sudden, you've had Databricks, which has been closed source for years, but you've got something like DataFusion Comet, which is going open source. We're getting all of these really democratized, phenomenal open source query engines based on Rust and based on the Arrow ecosystem that are processing data much faster than we did before. And you can now bring your own compute to all of these problems. It's really phenomenal. I think even beyond that, kind of taking that one step further, you're starting to see the potential for a lot more GPU data processing. So obviously we're using all of these GPUs for AI training and inference at the moment, but if there ends up being a glut of GPUs in the next 5 years, I really wouldn't be surprised at all if a project like NVIDIA Rapids, which is a Spark accelerator based on GPUs, ends up taking off, and you see that these gigantic chips that are phenomenal at parallel work end up being able to handle column batches really well, and they start becoming more popular in data processing. To that end, I think other people have kind of thought that same kind of, maybe GPUs are going to do a lot more work, or maybe we need to just, provide easier access to parallel data as quickly as possible. You're seeing kind of a small revolution in file formats at the moment. So for like a whole decade, Parquet was the de facto standard for how you're going to store all of your data for file formats. And then now you're seeing file formats like Vortex pop up, LanceDB. There are a lot of academic ones. There's one called Nimble, F3. And basically the gist there is that you want to limit the amount of black box encoding of data that you're doing, whether that's gzip or snappy or something like that, and instead use all of these new kind of groundbreaking lightweight encodings, which isn't going to keep your data as small, but it's going to mean that there's no big decode step of a large compressed block of data that you have to do before you can start reading data. So it's really good for random accesses, things like that. You may also have more flexibility in designing your files on disk, which might be really nice for something like multimodal data. Open source table formats are starting to support this in terms of, Iceberg maybe supporting split files for different columns of files. So I think the AI evolution in multiple different ways, whether it's new chips or it's just new data access types, has given way to a lot of really interesting trends in the space. And then also you're just seeing a lot of movement kind of away from these JVM-based applications in favor of Rust-based applications, which seems to kind of really be the language of the future. And then finally, I think another really big one is that everyone has kind of moved away from this concept of using local disks in the cloud. It seems like a lot of people are building architectures with object store as kind of the backing store of all state. Pretty much all local disks that I see at this point in new kind of groundbreaking data systems are ephemeral caches, maybe NVMEs or something like that. Maybe for machine learning, there's a little bit more use there of having NVMEs and having that be the actual source of truth of data. But for a lot of these new systems, whether it's a database or a Kafka-compatible system like WarpStream or something like that, you're seeing a lot of people just directly writing their data to object store, and if local disks are involved, they're solely there for the sake of caching. It provides a lot more availability. You don't have to worry about random disk failures. You know that something like S3 is really, really good in terms of keeping your data secure and safe. And then in addition to that, it's just generally cheap, right? It's 2 cents a gigabyte to store your data. You're not paying any cross-AZ replication fees within one region of data. And so a lot of people have started to opt towards that architecture, and the latencies on those systems have gotten really low as well for object stores.
Well, also you don't get paged for a whole huge subset of problems too, which is
right.
really good as well. But
hopefully.
Wait, I wanted to ask, the first sentence you said to the answer was that can you repeat the first sentence actually? You said something about column batching. So you'd only process columnar data, is that what you meant?
For sure. Yeah, I think, for a while we've had lots of older systems that operate on data one row at a time. So an example of that might be Flink. Flink pulls in a batch of data from Kafka, but then ultimately breaks it down into their internal row data model, iterates over it, does what operations they need to do. And what a lot of people in academia and generally, just more experienced folks have found out in the industry is that if you batch up this data and you organize it into column buffers, so for example, Arrow data in memory, you're able to get much better CPU utilization by operating over every single column one at a time. It's kind of like the same idea behind storing your data as Parquet on disk, but then all of a sudden, for some reason, if you're looking at a Spark application, it'll read all of this columnar data from disk, and then it'll transpose it back to rows, operate on each row one at a time, and then potentially even write back data to disk in a columnar fashion. Yeah. So there's a lot of wasted work both in that transpose, but then also there's actual benefit in being able to do this kind of micro-batching of data and processing it a little bit at a time.
And why was that? Why did Spark work that way? So to understand a record, right, you need to know every column basically, because the human abstraction is like some record that has like one of every column.
I think that is a fair point, so for starters, you don't necessarily always need every column of the data, right? If I persist a big data set and it's got thousands of columns and I'm doing analytical work, maybe I only want 3 or 4 of them. So that kind of gets bought for you by Parquet.
I was asking more like, why do you think historically that was the case?
Probably just developer simplicity.
Right, the
easier to think
model.
about. Yep, writing for loops.
Yeah, for loops are great.
They are great. Don't get me wrong, I definitely prefer to write for loops than deal with Arrow.
And when you say the future of data, we're talking about big data here, right? Because all of these optimizations only apply and give you practical benefits when you're presumably processing a lot of data. Do you have like a number you kind of think about? Like for example, let's say I have like 1 megabyte a second, or like whatever that amounts to in a day's worth of data. Would you still use these same techniques there?
That's a good question. So obviously premature optimization is the root of all evil. That's a quote that many software engineers want to live by. At the same time, I think there's a growing trend for people to say, you know what, this new technology that is for data processing, take DuckDB or DataFusion, for example, which is a query engine that you can run on your own computer. People are now starting to say, you know what, even for small data, these things are so good that I don't even need a query engine anymore. I can actually just run them on my 100 gigabyte data sets that are stored on S3, and I don't actually have to introduce any sort of Spark or distributed compute to actually do that. Generally, when I'm thinking big data, I'm talking, queries that are in the multiple terabytes of data or something like that. But I would agree that if you're persisting a megabyte per second, you can probably use Kafka like we have been doing. I see there's a trend to even use Postgres as Kafka. I think you've posted about that on your own LinkedIn. So there's always going to be this group of people who are saying, well, yeah, you're kind of over-engineering and over-optimizing this fairly simple problem. I think for what I'm interested, I really care about data at the frontier, especially as data usage continues to grow in this new AI era. But you're right that for the average company, which is especially small and doesn't have that much data, a lot of this may honestly be redundant. A lot of you may be better off sticking with the tried and true systems that are going to get the job done, have much better open source ecosystems, better third-party connectors, better support teams, things like that.
Yeah, for sure. That's what I mean. Like, I just want to bucket the conversation so we know sort of like what use case we're talking about and what
for sure
we aren't. So, what got you in the space? Can you tell us a little bit about yourself, your history, and yeah?
Yeah, for sure. I have a weird background. I don't have a very decorated background or anything that I can go flex about. But basically, before I started work, I used to be a software engineer at Google. Before I started doing that, I decided I wanted to study a little up on distributed systems. So as part of doing that, I made a YouTube channel called Jordan Has No Life, where I've posted, at this point, multiple hundreds of videos about both distributed systems, passing system design interviews, and now these days it's more so focused on some personal projects that I want to do in the data space, because I've kind of fallen in love with the data space. So I was kind of working on building data pipelines at Google. That was the main focus that I had there. So I got to learn some data principles behind, making certain batch computations a little bit more efficient. After that, I decided that I wanted to move to the high-frequency trading industry because I'd heard it was a really interesting place to be. There were some very cool engineers there. And I've had a really good time doing that. So the last couple of years, I've been working on a data team at my company. And so I've gotten, a chance to really get some pretty good deep understanding of Kafka, Spark, Flink, Iceberg, technologies like that, and start to get integrated just a little bit into the open source community. Like my company hasn't really fully dipped their toe in that water, but I've gotten the opportunity to interact with a lot of people who are making cool decisions in the open source community. And I think it's given me a little bit more insight on, definite trends in the industry. So, for example, I went to the Iceberg Summit last year, and a lot of the opinions that I just listed in those kind of first 5 minutes of our conversation are directly from the conversations that I've heard from a lot of the people who are really making waves in the data community.
Got it. That's really interesting. I have a lot more questions after this answer. Can I ask you a little bit about your work history? If you can, let me know if you can share anything. But like, for example, you said high frequency trading. So whenever there's a data team in a high frequency trading environment, I assume you're not in the critical path of the trade being made, which requires like milliseconds or even microseconds or whatever. Is it more like what kind of work does a data team do at a high frequency trading shop? Is it like offline analytics, or is it like backtesting ML models or whatever? Do you have any good examples?
Sure. Yeah, without going into too much detail, just because I'm not 100% sure of what I should and shouldn't say, our team is mostly focused on offline analysis. And what that really means in practice is just we publish a lot of data. We want to do a lot of analysis. And in order to do that, you need to build high throughput systems to handle all of the logs and metrics that you're publishing and be able to return that back to your user. So, we really care about being at the forefront of open source technology. We are not on the cloud simply because it doesn't make sense for us economically. We already have some data centers. And so being able to self-host things and, being able to run them ourselves and kind of improve them ourselves is a really important thing to us. So I'm mostly going to leave it to that just because, again, I'm trying to be kind of conservative about what I say here. But I think our data stack probably aligns with the data stack of many big tech companies. It's just a matter of, the actual data itself that's a bit more sensitive.
Yeah, for sure. And similarly at Google, was the stack somewhat similar, or I guess more proprietary? And also like some common use cases at the data pipeline team, I think you said at Google. Is it really like a central data pipeline team, or
it was not. Oh, I'm sure. So marketing data specifically, Google, you're right, completely proprietary. They have contributed to many open source tools in the past, but I would say the majority of their internal uses are proprietary tooling. But at the end of the day, if you're still interfacing with something with SQL and it's still got some sort of query profile URI, a lot of the principles are generally the same and applying to one another. I think Google implicitly has kind of been pulled into certain open source waves because they have a lot of customers on GCP that are actually asking them to integrate with open source projects. So for example, if I am a Google customer and I want to use BigQuery, maybe I want to use BigQuery to read my Iceberg tables, and then simultaneously I want to use Spark to read those same Iceberg tables. So I think they've gotten a few of those requests, but the data stack that I was working with at Google was proprietary. A lot of just big SQL jobs and figuring out how to optimize those sufficiently, whether it was, organizing the underlying data a different way to index it or co-partition things or optimizing joins to use a broadcast versus nested loop join or something like that.
And at a high general level, do you have any opinion on open source software versus proprietary in terms of, obviously we all love open source, but in terms of, would you say like that the proprietary one is generally a few steps ahead of the open source, or is it the opposite, or are they equal?
That's a good question. I think, generally speaking, companies take things to be proprietary when they feel like they can compete on them and are better than other companies. So for example, Databricks feels like it has a really great query engine, so it doesn't want to open source that. That's its edge. At the same time, I'm heavily pro open source because I think that it reduces the opportunities for things like vendor lock-in and technology lock-in. So for example, before, if someone was storing their data in BigQuery, that might have used a BigQuery proprietary file format and table metadata layer under the hood. Now BigQuery has to use Iceberg, which means that if I already have my data in Iceberg tables, I can much more easily switch off of Google Cloud onto Azure Cloud or Amazon or something like that. I just generally think it's a good thing to not give the cloud providers too much power over your individual data because they definitely want to take it where they can. They introduce a lot of artificial charges in order to keep you on their platform. If you look at something like egress costs, the second you take your data out of AWS, they start charging you multiple cents per gigabyte, which is kind of ludicrous when you think about it if you're really working with big data here. Even besides that, I just think that OSS is really great because you get the chance to work with some really phenomenal data mines from other companies that I normally wouldn't have the chance to work with. Like, I have a ton of really smart people at my company, but there's also experienced data engineers who have kind of been at the forefront of all the advancements in the community. They're working on projects like DataFusion or Iceberg or DuckDB or something like that. And, it's really awesome that their work is democratized enough that I can basically just go send them a Slack and they'll probably actually respond to me. So, for example, I've Slacked a couple of times with the creator of DataFusion, and, he doesn't care at all, and I'm sitting here freaking out about it. So I think it's really fantastic.
That is really cool. Yeah, that was a great point about the sort of almost like selection bias of what's proprietary in a company versus whatnot. So I guess it makes sense what you say. Like it should be either competitive or a few steps ahead, assuming the company is rationally thinking. Yeah, you want to say something?
Yeah, I was going to say, even though it's true that some companies do operate under that model, I think there are others that are actively kind of trying to dig out of that because they recognize that maybe it's not their moat. So, for example, Apple is maintaining DataFusion Comet, and like Apple is not like a Databricks or a Snowflake type of business, right? They don't want to make a query engine, but the reason that they're maintaining it is because it allows them to get open source support from other people to get access to Databricks level tooling without having to pay, Databricks or Snowflake level pricing. So I don't think Apple is ever going to try and monetize something like DataFusion Comet. But the beauty of it is that, certain companies who don't want to make it their moat, might open source something and say, we're going to get everyone on this, which is really nice. So, my company implicitly benefits from things like that, which is really great.
Yeah, well, I don't want to take this into an open source discussion, but, something on my mind with open source in general is not only how does AI change it, but also how, do you really need an open core business model? Let's say for Kafka, you needed a Confluent to drive the project and become a unicorn, etc. For Kafka to be so successful, if Confluent was not a unicorn or if it did not exist, the project would probably be just 1/10 of what it was. At least that's how I kind of think of it. And when I think about, let's say, Iceberg, for example, I guess Iceberg is more competitive, or we have Snowflake and Databricks compete on committers. I think most of the committers are probably from Databricks after that Tabular acquisition. Not sure if you know any numbers.
Yeah. I think, I was just messing around recently because I was kind of trying to get a sense of that. I would say Databricks definitely dominates, like the, project membership committee. There are a couple of high Snowflake guys on there. I think a couple of Microsoft ones as well, and maybe one or two on Amazon. But it definitely feels like it's dominated by Databricks and Snowflake. And, it actually taught me, I kind of understand the utility now of buying a company like Tabular, because when you're the company that runs the open source project, you can iterate on it way, way faster. Whereas me, I'm a pleb and I have to go the old-fashioned way of trying to convince a bunch of people to get stuff done. They still do as well, and it's part of kind of the ethos of the Apache project to have to get everyone on board. I think it's a lot easier, when you're all kind of working towards that one company goal to get that done.
Yeah, I think you're almost like buying the time of the committers. I think, being a committer myself, being in Confluent and playing those two roles of advanced Confluence, proprietary engine, and also contribute to the open source, you're fighting a very hard battle, right? Because you're being paid for 8 hours in the day at least to do whatever the company mission is. And if that's different from the open source, then the open source becomes almost like a second job, and it's really hard to juggle both. So obviously, if a company can pay for the 8 hours of prime time to focus on whatever they think is important, they not only get to get that important thing done by somebody high up in the project, but also they prevent the competitor from buying the same guy and having them spend their time on something else.
Right, exactly. That's a good point that you make with Kafka as well. Did Confluent maintain their own fork of it as well if they had to, really iterate quickly?
Oh, definitely, yeah. They forked it and they changed quite a lot. So much they call it another engine almost. Well, not almost, they do. That's always been the case, but they were playing both sides. They contribute very heavily to Kafka, even as part of the company's OKRs, quarterly OKRs. They would still have advance this, get this open source feature out. So they were a very good steward.
I think it's a similar situation with Databricks. From what I understand internally, they've kind of been trying to fuse Iceberg and Delta Lake based on some of the people that I've spoken to there. And they may have some features that they support on their tables that are technically Iceberg tables under the hood, but have some extra stuff going on. And they've also bought a couple of companies that are Iceberg adjacent in order to kind of try and improve their internal offering.
It's a real tug of war. I think it's a really hard fight to fight, basically, because if you don't support the open source project, then that kind of withers away, and eventually it's going to lose to something else. And if you don't support your proprietary offering, then somebody else is going to make money off of the open source, and they're not going to buy your thing. But yeah, I think there's a lot of really good thoughts on the matter. I think. No, I can't remember the article I read about. But anyway, okay. So to talk more about you, because you're the guest on this podcast. Can you tell me a little bit about your personal projects? You said that recently you've been doing more personal projects than just general videos. Like a few questions on that. First, what got you to stop doing the other stuff? Like, did you get bored of just teaching and explaining? And then, of course, what are the projects? And tell us all about that.
Yeah, I'd love to talk about that. So in terms of me kind of moving in this direction in the first place, so at this point on YouTube, I've made a series about kind of introductory concepts to learning about distributed systems and systems design. It kind of starts out with all the concept of Martin Kleppmann's designing data-intensive applications, or DDIA, so I've kind of covered that in video form, moved on to maybe a few more systems that he doesn't really cover, where it's like, oh, like this is Postgres, this is Cassandra, this is Kafka, etc. He kind of goes more high level about them without naming names as much for systems, and it's also an older book at this point. And then I've covered probably, let's call it 30 different systems design problems. And what I've more or less noticed as I did that is, for starters, the systems design problems, a lot of them, I'd say you can pretty much break them down into like 8 or 9 different patterns, and I have a video about that on my channel, but a lot of them basically come down to this index pattern where you want something read optimized for the majority of your users, but the write to get it there is tough. So think of like posting on Twitter, for example. If you have 1,000 followers, you want to post one post to Twitter, and then you want that post fanned out to all of their inboxes or their particular cache, so it's got better patterns when reading the data. And to me personally, I could optimize for views on my channel, and I've kind of throughout my channel's history made multiple decisions to not do that. Partly because I don't think it would benefit me as an engineer. I'm still pretty early into my career. I've only been working full time for 4 years, and I don't think it would benefit my viewers either. I think it's really easy to just cover the same redundant stuff over and over and over again, and people will continue to watch it because I think people really eat up interview content because it makes them feel productive, and ultimately everyone's really attracted to a job with a higher title or a higher salary or something like that. But I also intrinsically really care about trying to improve as an engineer, and so that's what steered me in the direction of doing more personal projects. At first, I told myself, I'm going to manually code these out. It's going to make me a much better engineer, et cetera, et cetera. And then probably, I've only been doing this the last, let's call it 9 months. I think probably 6 months ago, I got to the point where Claude Code has changed my job, where I'm barely coding anymore, because I'm legitimately able to do certain things like 10 times faster now. And so, unfortunately, I've kind of come to believe that the abstraction layer in which engineers are going to work in the next 5-10 years down the line is going to be probably at English again. And I still think there's tons of value in having a good distributed systems background. I don't think the problems that I'm trying to solve with Claude Code are ones that any engineer can just pick up and immediately know how to do. But things have changed a lot, and it's pretty interesting to see how that's
gone. Did you say in 10 years?
I mean, could be 1 year.
Months. It's more like 10 months, man. I don't write code anymore. I've stopped. I don't do it professionally, but it's improved so much. I didn't mean to ask you about AI. I guess also, when you become 10 times more productive, I've seen that also the ambition rises 10 times more and potentially even higher sometimes. I've seen myself, like my own progression, again, last few months has been this phenomenon where I code a lot more. Well, I code, like Claude Codex code for me a lot more. And I feel like I'm doing just 10 times more projects. And a lot of times, by the way, those things are I wouldn't say useless, but of questionable value. Obviously, like when it takes 10 times less effort to do something that wasn't worth the effort before now becomes kind of worth the effort. So you get a lot of these kind of throwaway things or toy things, but it's really gotten so good. I'm not sure I can pinpoint when it became so, but I definitely find myself talking a lot in English. And Well, the way I conceptualize this for myself is I think we all just became tech leads and managers. If you think of some sort of classic company, like a very high, like let's say architect or maybe even tech leads, right? They don't write code, they just review. Like when I was a tech lead at Confluent during my last year, I think I barely wrote any code that year. That's the reason why I quit, by the way. It was really boring. But all I did was just review like incidents, I would review design documents, and I would review PRs. And I will just give English guidance to the people on how I think we should do this, or like I would, ask questions of like, hey, maybe we should investigate this and check this versus that, etc. And it's really the same thing I'm doing with Claude today.
Yeah, I not only agree with what you said. To take it a step further, I think I'm doing the same thing where I'm just looking at code. I'm looking at the output of Claude and saying, does this make sense, or are you hallucinating? And now I'm mad at you. I think we're going to probably have to change how code review works fairly soon, because in the open source projects, which I follow along about, the human is the bottleneck at this point. Like, people can come along and churn out so much code with Claude that it's not really feasible for 15 people in different time zones to just kind of figure a way to merge all of that in. I have what I would hope is a pretty impactful change outstanding in DataFusion Comet at the moment to enable writing Iceberg data. And this is no shade to their committers. It's 5,000 lines of code. As a reviewer, when I see 5,000 lines of code, if someone ever sends that to me, I'm like, I'm like angry about it. So I feel like we're going to have to figure out kind of a new abstraction layer for code reviews to take place as well. And maybe that's, we discuss the planning document together, and we review that, and we review it all in English, and then, whatever the code is that gets written, we're going to have test cases, we're maybe going to have some benchmarks to validate that everything's working fine, but it's okay if we lose a little bit of track of the actual code itself, and maybe the AI does repeat itself a couple of times. Maybe that's okay. But, us kind of hanging on to, like, we need this extreme control over our code bases, I think is starting to be a thing of the past already. It's really tough.
It's absolutely dead, yeah. I think the problem is how you reconcile that with the legacy code base. Because if you're starting from scratch, I think you can make it work. But when you're adding on top of a legacy code base, I think it becomes difficult. There's two sort of big problems here. One of them is that, devil is in the details always in the code. Like from reviewing like so many PRs in Kafka, I always know if I don't review the PR properly and I sit down and read every single line and be very focused while I'm doing it, some bug is gonna creep up. And if I do it focusedly, I usually catch a good bug in the PR review. I always remember, I would rate my review if it's good, if I catch a good, like, subtle bug that nobody else would catch. And I had a few of those. So that's where I see the value of actual good code review. So I still think it's very valuable if you can afford the time. It's kind of a matter of, is it worth the time? And in infrastructure software, in infrastructure open source software, I think it is, because in something like a Kafka, I don't know how used DataFusion is, for example, but I guess Kafka Iceberg, you introduce a bug there, you're having a lot of problems. You're going to have a lot of problems if it gets shipped, people start adopting it, especially if it's a latent bug that gets caught, let's say, a few years later or even months. So the whole problem of this is that there's a symmetry in both sides. There's a symmetry in how little effort it takes me to write up some slop that ruins your project with some nasty bug, and how much effort it takes you to actually catch it. And then the other asymmetry is, it's very easy to release new features, but it's way more effort to release stable features that don't really, crash the project or create any sort of problems down the line. And it's also because there's such a big lag from where like open source software moves very slowly. Let's remind ourselves, it's not like an agile workflow in a company where you deploy every week. No, the open source project releases a new version, let's say every 3 months or something like that. Then from the time you released it, 3 months have passed since the PR has been merged. Then how many months does it pass until the community actually sort of adopts the brand new version? It can be years. And
So I agree with everything you said. I'm going to push back slightly on one point. So I 100% agree. If you introduce like a bad bug in critical infrastructure software, it's over. That's potentially millions or hundreds of millions of dollars of data that could be wiped out very, very quickly. I think the area where I push back on this is saying that we, like obviously humans can catch bugs, but I think there are other ways to catch bugs that are maybe more automatable, that may be more, let's call it AI native for now, but really it's more automated. So one example is a while back I was watching this talk on a piece of software called Tiger Beetle. It's a financial transactions database. And the way that Tiger Beetle does it is they have a gigantic test suite of a bunch of fuzz tests causing random conditions, causing all sorts of random race conditions, or attempting to interleave all sorts of transactions. And I think that, if anything, the direction that we need to evolve in is doing more due diligence in developer tiers, integration tests, like canaries, things like that, having all of these randomized chaos monkeys, and, really documenting out our edge cases. And I think part of the reason that we didn't do such a good job of that in the mostly human coding era is because it sucks and no one wants to do it. but one of the really nice things about having agentic coding is that you can be like, hey, build this test suite out for me, and here's how I want you to do it, and it's faster to do. So you're right, it won't catch every single human bug, but neither will humans. So there are inevitably going to be bugs.
Absolutely. Tiger Beetle seem extremely cracked at that. I remember reading their stuff a few years back. Another thought on this, and again, I didn't mean to talk about AI, but that's the topic of 2026. Not only can the AI create a test suite, but the real value, I think, comes from the AI analyzing the test failure. So again, from my experience at work, we would have integration tests, we would have system tests. They would inevitably be flaky. And you end up losing so much human time in just debugging the same flake over and over and over again. And then eventually somebody gets his time prioritized to fix the flake. And then they invest so much time over and over and over again to reproduce the flake and then get the flake fixed. And maybe you fixed it. And that's just one example. That's just one branch of one bug that causes a flake in the test. Now imagine like a complex system that has many of these. So you kind of have this pushback of like, hey, I don't really want to introduce a new system test. Like, this is going to be so much work to maintain over the years. And, but AI fixes all of this. AI can review the bug. Like, it can try out any bug in seconds or minutes or whatever, automatically, asynchronously. You won't even know that it's a flake or not. It will tell you, well, hey, this is most probably a flake, this is not. It can try to reproduce it and run it in parallel as many times. Again, there's not a human in the loop that needs to stay at the computer and have this task where, okay, every 30 minutes I'm going to refresh this test and see if it failed as a flake or not. Because not to mention how much of an awful context switch that is, right? Like, you're working, coding something up and then, okay, like, let me see if this test was a flake or not. Okay, I'm going to run it again. You focus on something else and again. And so AI can, again, review catch the flake or not. It can parallelize and run and try to reproduce it, and then it can fix the bug in the flake. So from that point of view, I think where I'm really excited about what AI does is not just writing the test cases, but also really maintaining them and making it maintainable to have 20 times more tests than before.
Yeah. Well, you know what? I think that's a good bridge back, because I know you were starting to talk about my personal projects, but I think this describes kind of the ethos or mentality that I'm taking when I try and build them out, which is I am maybe having a little bit of trouble with existing open source projects just because of the way that they're set up. It's really hard to contribute to them. I can build as many features as I want, but ultimately I need some guy in Japan who doesn't speak great English to review this thing. And, he's going to knit me, and then I'm like, all right, well, it's 24 hours. I got to go back to you. So I'm trying to start one up myself. I really hope that I can eventually have basically an AI PPMC for it. And I was trying to think about, hey, what's the most kind of verifiable project that I can think of that's still complicated from a technical perspective, but also might be one where there's a lot of existing code sources that I can pull from, and I can give some clear tests and some clear North Stars for AI to solve. So I think the thing that I came up with that I'm very excited about and I'm starting to work on a lot is trying to accelerate Flink. So I mentioned DataFusion Comet earlier on this podcast. DataFusion Comet is a Spark accelerator that uses DataFusion on every single executor node to speed up operations.
Can you define DataFusion really quick for anybody who hasn't heard of it?
Absolutely, good point. DataFusion is an embedded query engine, meaning that rather than standing up this dedicated cluster of nodes to run a bunch of SQL queries for you, DataFusion is a library that you can call from any given process. It is extremely efficient. It is built in Rust, and it generally operates over these Arrow column batches, where Arrow is a standardized memory format for data that lives in columns as opposed to rows. So, in normal coding, you represent your data row-wise, you create some sort of object, you iterate over it with a for loop. Arrow data is particularly useful because it is organized in these column batches. So I have basically a bunch of arrays where every single array is one column of a 2D matrix. What's really nice about using a standard format to represent that data as well is it means that when I'm using a project that requires interoperability, so for example, if I have Flink calling code in Rust, I can pass an Arrow batch that's in Flink over to Rust and have Rust operate on it without copying the data whatsoever because it's a standardized format. So that's a really, really amazing thing, and it's become very popular in a lot of common data projects.
Great answer. And when you say not copying the data, zero copies, so what does that actually look like process-wise? Like, it's just...
Yeah, there's an Arrow CData interface, basically, that allows you to pass a pointer to an Arrow buffer between Java and Rust in the example of my project.
Okay, cool. Okay, so please continue with the project.
Sure. Basically, Flink is a distributed engine to perform streaming processing. So it'll read data off of something like Kafka. Maybe it'll shuffle it, maybe it'll transform it, and then ultimately it'll persist it somewhere else to either Kafka, maybe an Iceberg table, maybe a database, something like that. But internally within Flink, I'm going to try and accelerate that by basically saying, all right, Flink creates a SQL plan, just like any other SQL operator. I'm going to replace nodes of that SQL plan with DataFusion nodes, where basically the data is transposed to Arrow batches, operated on within DataFusion, and then ideally chained into subsequent DataFusion operators. So for example, if Flink says, all right, I need you to filter this data to get rid of rows where x is less than 5, and then I need you to project this data to only keep the column called name, I'm going to ideally have two chained DataFusion operators that are doing that for me completely on the Rust side without ever going through the JVM. It eliminates a bunch of overhead, and additionally, it also just means that you can, again, iterate on Arrow batches, which is provably more efficient, and it's where a lot of these modern data architectures are starting to move.
But are those running in regular Flink tasks?
Yep, so the task manager itself will simultaneously be calling via JNI to these DataFusion operations. Remember that DataFusion itself is just an embedded library, right, meaning that I can call via JNI to DataFusion.
Right, so your Flink job is basically like import DataFusion dot whatever. Like
effectively. A little bit more gross than that from a code perspective, but yeah.
And did you say that you're also, instead of like, what example can we use? Like if you have a map by and then a join by or whatever, or like come up with some pipeline, instead of having like two separate Flink tasks for each part of that pipeline, are you saying that you're doing them all inside a single DataFusion node?
So basically the way that Comet works, and I'm taking inspiration from this for what I'm going to call StreamFusion, is you have a whole SQL plan, so you have a tree of operator nodes. You'll look at all of the nodes that are completely columnar, meaning that I can, recreate that functionality in Rust and DataFusion. And then you will basically pipeline those operations on the Rust side without ever passing the data back to the JVM. So for example, if I have multiple operations in a row that I've implemented the corresponding SQL code for on my end, then I can pipeline those results all the way through, which is really great. Right. The goal eventually is to basically implement a Rust operator for every single thing that can possibly be covered by Flink SQL, so that when you submit a Flink SQL job, I can give you a result with complete parity where the data is actually just flowing through Rust the entire time.
But that's all in a single task. It has to be.
It's right? Not a single task. This can be distributed as well. So like you mentioned, DataFusion is a library. But you can basically use individual DataFusion instances on each task manager to distribute these Flink jobs.
Interesting. Well, I guess I don't get the full picture then, but that sounds so. Well, from a practical standpoint, why do you want to speed Flink up then? I would ask, because I read all about how fast it is and efficient and etc. In what cases is it worth to squeeze that extra performance out?
I think you can make the case for pretty much any hardware that you want to squeeze out additional performance, especially given that compute prices are so high these days. Like, an increase in throughput also potentially means a decrease in compute used while maintaining comparable throughput. It's a very common pattern to basically persist data to something like Kafka, read it via Flink, and then persist it to Iceberg, because Flink is kind of that aggregation and batching layer. So there are many companies that are spending a significant amount of compute on their Flink clusters, my own included, and I think it would be a really positive thing to be able to refactor some of these jobs. I think in the age of big data that we're in, obviously everyone's running these huge analytical batch jobs in order to gain insights from the data, but I think it's important to note that there are a lot of companies who simply just need more throughput from their streaming pipelines because we're just persisting so much data. Like, I can only imagine how much data Anthropic has to, get, persist, and use in order to perform reinforcement learning on their data. That takes so much compute. I think even beyond that, it is kind of a nice sign for me to see that Viverica, which is kind of the commercialized company that pushes Flink forward often, has a closed source version of this. So, if you think of Viverica as like the Databricks equivalent of Spark, then their main product now is Vera X, which is a Flink accelerator. But they're not doing it open source. They're building their own engine, and I don't think it's nearly composable enough for other people to work on. And as a result, I actually think that means it's going to be harder to build with something like AI. So I'm trying to really stay on common existing popular open source libraries as much as possible. And so in that case, that means DataFusion, and then there's an existing Rust-based streaming engine called Arroyo. Arroyo was acquired by Cloudflare, I believe, a year or two ago, but their code remains open source, and you can use it.
It's not maintained anymore, though, is it? If I remember.
I believe it still is, to my knowledge. And if it's not, then Rising Wave certainly still is, and Rising Wave is another columnar Rust streaming engine. But basically, because that code is out there in the first place, it gives me a really good reference point to kind of point Claude to and say, hey, this is exactly the type of operator that I want. It operates on column batches, it delegates to DataFusion where possible, and it serves as a really good reference point for keeping the speed fast.
Got it. Yeah. My bad, it is maintained. Last release was December 25.
Sweet, okay, good.
I see some commits. I don't know how active it is compared to before, but it's definitely not.
That's very fair. Honestly, if it's not, that may benefit me.
I think it's a great choice to build in an AI native way of composable features. Is StreamFusion live? Is the project working, or is it still like an idea you're iterating on?
I quite literally open sourced it an hour ago. From a code perspective, no, it's not there. I would not recommend trying to productionize it yet. At the pace that I'm going, give me a month. So there's one common benchmark called Nextmark that all the streaming platforms use. So it's kind of like the TPCH equivalent for streaming. And there are very common Nextmark results for Flink. And so my North Star that I'm telling the AI, hey, I want to eventually get here, is I want to be, noticeably better on the Nextmark benchmark than Flink is, running on my same computer, being sure that I'm kind of picking up those performance speed-ups that I believe should be there.
So congrats on the open source. We're definitely going to link it.
Thank you.
So it's open source. Does it work at least? It's a working version, right?
Yep. Worst comes to worst, if code doesn't pass, or if an operator in your Flink SQL job is not columnar, it's just going to fall back to normal Flink.
Right. Have you done any benchmarks already to have some numbers to share with the audience, or is it too early?
I'm mainly doing local benchmarks using something called Criterion, which is just like a small benchmarking tool in Rust. I don't want to share benchmarks because it's not overly accurate until I really deploy this thing on the cloud. But, for example, just as a proof of concept, I was like, all right, I'm going to read a Parquet file using Flink. I'm going to write that same Parquet file back. And then I'm going to read it using mine and then write it back. So keep in mind, there's no transpose in reading the data from columnar, putting it in rows, and putting it back. I'm getting 5x performance on that. Wow. And that's the best possible case I could possibly get. I do not expect to get 5x performance here. I'm aiming hopefully between 1.5x and up. That would be phenomenal. Certain operators, I am seeing that level of speed up. Other operators, I am not, and that's where I'm going to have to like really meticulously profile and go through flame graphs and see what's actually using up that CPU time there.
Or the AI will.
I hope so.
So I hope I'm not being slow here, but I want to ask you
No,
again
not at
about the
all.
architecture, because I want to make sure I understand. So let's do Flink 101 then. Let's make sure I even know what I'm talking about. So an operator in Flink is like if you have a job that, say, reads from Kafka, filters data out, counts the number of data points, and then puts it back into Kafka. Those are 4 operators. You have a source operator reading from Kafka. You have a filter operator filtering the data, the stream.
Yep.
You have a count operator counting the amount of records, and then you have a sync operator that puts it back, right? If I
That's
understand correctly, in Flink, those 4 jobs can be, I don't know if they always are, but usually can be and would be run on 4 different nodes. Is that right?
Not necessarily. I mean, well, when you say nodes, do you mean like literal different computers, or do you mean just different operators in code?
Computers, usually.
No, not necessarily. So you can co-locate operators on the same computer. Basically, you have in Flink, you have a job manager, and then you have a bunch of task managers, and the task managers can, kind of host arbitrary code. Each one might run, to my knowledge, to be fair, I'm not a Flink expert, but this is how I understand it. Each task manager can run a subset of the operators, and then the operators themselves might be parallel and distributed across some of the task managers, and there might have to be some shuffle stages between operators in a given job graph.
Right, so you don't have to, but you can. The shuffle is what we call when you switch nodes. Was that right?
So shuffle would be
no, when you repartition.
It would be a repartition, yeah. So it's similar to a Spark shuffle. So it would be like, if I call key by on a Flink operator, then that would be invoke a shuffle, most likely.
So let's keep the example simple and avoid repartitioning or shuffling. Then in production, I would ask, or in practice, do you usually try to collocate a lot of operators together, or do you try to do the opposite and split them up?
I would think you would want to co-locate. So for example, let's imagine I'm reading data from Kafka. I've got 4 task managers, so 4 like nodes that Flink can do work on, and I've got 4 Kafka partitions that I want to read from, and I'm filtering the data, and then I'm projecting the data by adding 1 to some column, and then I'm putting it back in Kafka to 4 output partitions. I would think that you would want to read each one of those partitions on a different task manager, persist the data on the same task manager, and never do any shuffle between them, because typically in batch computing, and I believe it's the same for streaming computing, anytime that you're seeing a shuffle, it's less than ideal. I mean, sometimes you want to do it to balance out the data or remove any hotspots or something like that, but it is going to ruin your, it's going to hurt your throughput if you're shuffling data all the time. You want to generally co-locate where possible.
So just to say again, shuffling isn't shuffling the act of repartitioning the data.
Yes.
Just moving from one node to another, that's not a shuffle, is it? If 2 operators are in 2 other nodes.
It wouldn't be if you're not repartitioning, but even still, I would still think you'd want to co-locate.
Right, you want to co-locate to avoid the networking overhead and all that overhead of passing the data by. So then
That
from
I
that
agree
point
with,
of view,
yes.
I was asking for your project, because you're using DataFusion, it's basically a local library in the process. Does it, if I have let's say 4 operators, and are they if 2 are on 2 different nodes? So let's say 1 operator here, 1 operator here, 2 different nodes. Does your library still it? From what I understand, it would not work that way. You have to still pass the data by, obviously. So you can't do it the same.
You can do distributed operators still, because Flink is basically in charge of the orchestration of the shuffle. So the JVM in this setup is in charge of basically sending data between 2 subsequent nodes, and then we're just going to DataFusion and saying, hey, here's an incoming arrow batch, I want you to do something with it. So there is still a shuffle or a data passing mechanism in this case.
But then you touch the JVM by necessity.
I inherently have to touch the JVM, because for me to take all of that, sending things like watermarks and checkpoints out of the JVM, that's actually a significantly harder problem than it is to keep all of this state management, which is actually not the performance critical part of Flink anyway. So you keep the kind of tough state management that isn't performance critical, like just sending checkpoint from operator to operator in the JVM, and then you handle the actual really tough I'm running through a bunch of data and processing it in Rust. And the reason that works is that Arroyo's operators themselves use the same asynchronous barrier snapshotting checkpointing model of Flink. So as long as I can hook up the Flink checkpoint into the Arroyo operator, which says I need some sort of checkpoint, and fortunately that does work, then you find yourself able to build out a full system here.
Got it. So maybe I misunderstood at the beginning. Then I thought you were co-joining operators together in the Rust code, but rather it's just again separate. It's basically the operators rewritten in Rust, right? Is that a fair way to say it, kind of?
That I would say that is the most concise and perfect way to say it. So thank you for paraphrasing for me.
Yeah, makes sense. All right. Yeah. Well, I mean, Rust is great, and so that's your focus now on a side project. What about the Iceberg thing, the IceStream, I think it was called? What happened to that, and what was that?
For sure. So this is an interesting one as well, and I still think it's a problem. I would love to pursue it more. Basically, in Iceberg, the seemingly most supported open source way to stream data from Kafka into Iceberg tables is using Flink. So you'll write data into Kafka in small rows. You'll use Flink to potentially shuffle and buffer that data, and then all of your Flink task managers will, in lockstep, commit that data over to your Iceberg table. Now, let's imagine that we have an Iceberg table that involves upserts, right? So maybe I'm publishing a bunch of rows to Kafka. Every single row has an ID field. I can overwrite old rows with new ones by publishing a new row with the same ID to Kafka. The problem in Iceberg at the moment is that, when you want to upsert a row, you have to emit some sort of delete marker or tombstone for the old row, and then you have to publish a new row. So there are two types of delete markers in Iceberg. There's equality deletes, and there are positional deletes. Positional deletes is saying, I want to delete a row in file A, position 1. Equality deletes are saying, I want to delete a row where ID equals stamp. So equality deletes are much easier to emit from a stream processing pipeline because you don't actually have to read the table back in order to figure out where the old version of the row is. Does that make sense? Or am I losing you there?
Right, yeah, it's declarative, of course. It's easy to say,
Perfect.
I want this row removed.
Exactly. So it's a write-optimized thing, but it's much slower on the read path. When I actually want to query my Iceberg data, it's going to be much harder to actually figure out what rows to remove because I have to resolve them from my equality deletes. Right. So all this to say, this has kind of been a common problem, is how can we optimize this Iceberg streaming pipeline? So the way that I think many systems do it is they invoke data indexes, right? You still want to emit these positional deletes because positional deletes are more read optimized. At query time, all I have to do is see the positional delete, and then I'll say, oh, if this row is file A position 1, I just get rid of it. I don't have to compare it against all these other rows. So the way that people have been trying to do it, generally speaking, is you maintain some sort of index on the write path or the insertion side, such that you're keeping track of where all existing rows already live in the Iceberg table, and then you are able to basically get rid of them, or you're able to say, oh, I see this new row with ID stand. Where does the old row with ID stand live? I say, oh, it's in file A position 1, and then I emit that positional delete in lockstep. The reason that's efficient is because, again, this is an index, right? So if it's a bunch of sorted data based on that ID key, I can really efficiently pick out one row by binary searching the data or something like that. So I'd say the first person or the first company to introduce this type of software was one called Mooncake, or Moonlink was the software that they introduced. They got acquired by Databricks, I want to say like a year ago. To my knowledge, Databricks hasn't really rolled it out at scale. I heard about Moonlink's design. I was not really a huge fan of it for a couple of reasons. For one, everything that they did was change data capture through Postgres, whereas I just wanted data, to go directly to Kafka and have some stream producer. Number two was that in Moonlink, the actual writer of the data was the same one that had to be maintaining the index, and if someone else modified the Iceberg table, then that index wouldn't be updated, which I thought was problematic. So like if I wanted to update my table with Spark while I had Moonlink inserting into it, Moonlink wouldn't pick up the fact that I updated the table, and then we'd have a problem and its index wouldn't be up to date. And also Moonlink wasn't distributed. It ran within the confines of a single vertically scaled Postgres node. So I set out to solve all three of those challenges, And I do think that I've done it, but it's also the case that Iceberg is simultaneously solving their problem internally via the open source community. So I'll talk about what I did quickly, which is I wanted to be, like I mentioned, distributed, engine agnostic, and I also, as opposed to that Moonlink solution, which is kind of synchronous, right? As you write a row into the table, you're simultaneously looking for where it exists in that index. I wanted to make mine asynchronous, meaning I was going to allow you to publish an equality delete, and then down the line I was going to convert it to a positional delete. The issue with doing this type of thing synchronously is that, let's say I'm the streaming writer, I try and figure out where ID Stan lives in the table, and then someone else comes along and changes the table before I can commit my write. Now ID equals Stan might not live there anymore, and you have to redo a bunch of work. Right. So doing this type of thing asynchronously means that you don't have to worry about these types of race conditions.
Yeah, there's not this race that I've seen in some of these engines where you basically, I think, what was the name for this type of thing? Like a racing, I feel like there was a name in the Iceberg world for this type of thing, but basically where you have to race, and then if somebody races you to the right, then you have to refresh everything again, and you can have so many retries that really slow you down.
Yeah, optimistic concurrency control is what they call it. Yeah, so there's that problem with the approach, and I wanted to just make it as open source as possible and engine agnostic, meaning that I didn't want to build it into Flink specifically because there are still people who write their Iceberg data with their own JVM applications. Maybe they write it with Rising Wave, which is a Flink streaming engine. Maybe they write it with Kafka Connect. So there are many different ways of doing it. I didn't want to force people to one implementation, and I still wanted them to be able to edit their table using a batch job in the background as that happened. So what I built is called IceStream. Basically, all that it does is as a table updates, it's effectively doing change data capture on that table, looking at the new state, maintaining a secondary index in the background of what is contained in that table. That way, as you begin to emit delete files to your table, I can then look at those delete files, compare them to the state of the table as of the time those delete files were emitted, so using my index, and then really efficiently convert that equality delete to a positional delete. So I ended up storing this index in Apache Paimon, the reason being that they actually support storing index data on object store. And so it seemed more compatible with the ethos of people who are kind of running Iceberg tables, which is they want to use object store as their backend. And then I was using Apache Flink as my processing engine, but not necessarily one that you had to use as your streaming engine for Iceberg inserts. So basically you would deploy Flink in the background, you would point it at this IceStream jar, you would run this IceStream jar, and then you would continuously pull this table, building up your index and converting equality deletes to positional deletes. And I have some benchmarks to actually prove that, at certain partition sizes, for example, for a 10 gigabyte data partition, I can convert equality deletes to positional deletes, 2 or 3 times faster than doing it without an index, for example.
That's a very interesting story, and the story of how you chose Paimon was really interesting because you used Cassandra first of all, right?
I did, yeah. Good question. So originally I was going to use Spark because Spark is a batch engine. It felt like the more natural thing to use here to kind of maintain this index and do these positional delete conversions. So I was doing some research online about how I could do a nested lookup join in Spark. So what that really means is in Spark you want to be able to take one data set and then join it to a second, much bigger data set, where the first data set, you're looping through it one row at a time, and then you're hitting an index on the second data set, because that's effectively how you're going to get this best possible performance by indexing all your Iceberg table rows. I found that Apache Cassandra had the best connector in existence, known for that, and believe it or not, it was actually written by one of the main Iceberg contributors today, and in practice that worked nicely, but when I spoke about it on Reddit, people basically said, hey, if we have to deploy Cassandra, that's a non-starter for us. We don't want to deal with a database. And I'm not necessarily 100% sure if it was just Cassandra or they would have said the same thing even if it was Postgres. But I didn't want to build out my own Spark connector for Postgres. So instead, I found Paimon, and then it seems that Flink, out of all the kind of like batch computation engines, has the best integration with Paimon, which is why I switched to Flink instead of Spark.
And Paimon is basically a turbo format optimized for streaming rights.
For all intents and purposes, I'd say it's the Chinese Iceberg. And frankly, it's moving really fast, seemingly. Like I submitted a couple of OSS changes to it just to kind of optimize this nested lookup join in Flink, where you have one row and you're saying, can I join this really quickly to an index table in Paimon? And it was like a weekend at 10 a.m. my time on Saturday, and someone in China was reviewing my code and letting it go through. So
that's nice.
Say what you will about the 996, it gets stuff done.
Well, 996 gets stuff done for sure. The Chinese Iceberg, but no, it's a different architecture, right? From what I remember, it was optimized for faster writes, and I'm not sure where the other trade-off is in the reads or in the way it stores data, etc.
That's a good point. So I won't claim to be any sort of expert about Paimon. To my knowledge, it's got a couple of slightly different things. For one, the main feature that I really cared about was the ability to have indexes on a table, right? Like Iceberg doesn't support a primary key table as a first-class citizen. It allows you to sort tables, but it doesn't make any guarantees about whether a table is sorted at a particular time. And so as a result, you can't really rely on it in the same way that you would a traditional database index. None of the engines that read Iceberg are saying, oh, I'm going to binary search this data to find one particular row that you gave me. It's always Parquet row group filtering. So Paimon actually does have that, like first-class principle of saying, we'll allow you to have a primary key table. And not only that, but we're going to guarantee that data is sorted a particular way, which makes it so that engines can more efficiently query for it when you're doing single key lookups like I'm doing. Besides that, I do think that Paimon, was kind of more so built out as like a streaming format for Flink, and I think what that meant in practice was that Flink always kind of had the full support of the table. You would do all of these small like buffering of data and memory before writing, so you get optimized file sizes. Beyond that, I don't know a ton, but they do a lot of table compactions as well, in the same way that Iceberg does, to be fair. It just, to me at least, it resembles more of like this LSM-style database where you have multiple different levels or layers of compaction, so you can take small files and compact them at a more frequent granularity rather than always doing like a full gigantic compaction like Iceberg does. And yeah, they've got some really cool feature sets. Like I think it's a newer table format, and it seems to have been developed pretty quickly.
I'm not even sure it was newer, honestly. If I remember correctly, I think it was around the same age, but I might be wrong.
Really?
Honestly,
you could be right. I may have just heard later.
But basically, it's definitely just less popular. And that's another question I wanted to ask you on, because I'm not sure if it's more mature or not. I'm not sure if that even matters nowadays, but I feel like we live in a day, especially now with AI, but even before, where distribution is everything and the network effect is everything. And Iceberg obviously has the biggest distribution, the biggest network effect today. Every project sort of supports it, and so many people are working on it. And then close second is Delta Lake, which is also very well supported. And you mentioned some of the newer, I think you said file formats at the start. You mentioned LansDB, which is, I understand, both a file and a table format. We have Paimon as well. So we have all these new table formats coming out as well. How do you reconcile this? Like, what's your opinion on the table format world?
That's a good question. I also feel like I probably align with the majority of the community when I just say, choose the popular one, because it seems like a lot of the gaps that, say, Iceberg has versus any of the other table formats, there's already someone working on trying to get it there. I think,
like you, right?
You mentioned. I'm trying. Various degrees of success. But even for indexing the data on the insertion path, there are active projects within Iceberg to make that happen right now. And the only reason I did what I did is I was just convinced, hey, I can probably get this done and in full production a year faster than Iceberg might be able to. But the truth is, I think trying to cut off an open source project by a year before they fully support something is maybe not the best way to make impact in the data space. I should try and do something bespoke, hence my new project. But to your original question, it does just feel like Iceberg is kind of winning out. Databricks purchased Tabular. They're effectively merging Iceberg and Delta. I don't really see too many new projects that are using Delta these days. Hoodie is still an open table format that at times is actually developing kind of quickly, and like they've come to integrate new formats like Lance or Vortex or something fairly fast. But at the end of the day, if I look at the size of the communities, it just seems like Iceberg is winning out long term. And I know of already, I think, some legitimate companies that do already have a ton of their data stack in production on Iceberg.
And I want to pick your brain about Iceberg usage. So presumably, you probably use it at your company, as you mentioned. But in general, from who you've spoken to in the Iceberg summits and just people who are interested in projects you work on, how do you see Iceberg being used in production today? For what sort of use cases is it used for?
That's a really great question. This is basically all just based on the conversations that I had at the summit. Just in terms of adoption, I think Databricks and Snowflake are obviously hugely invested in Iceberg at this point. All the cloud providers hugely invested in Iceberg at this point because of what I mentioned. Everyone keeps coming to them, asking them to support Iceberg tables so that they're less likely to be locked in. So Microsoft, AWS, and Google all have big Iceberg presences. I've spoken to multiple people at Apple who are using Iceberg for their internal data. And so in terms of what they're actually using it for, I think it's mostly still this kind of batch analytics case, but they're trying to unify it more towards low latency accesses and streaming every day. Like I mentioned, there's this open source effort to get there. There's some private companies like Firebolt, for example, that to my knowledge is trying to do kind of like these low latency Iceberg reads for dashboards. They originally had their own format. They're now moving towards Iceberg. There are these open file formats like Lance and Vortex, etc., that are actively pushing to try and get themselves involved in Iceberg. Iceberg just implemented a new interface to make it so that they can have a lot more file format support rather than just Avro, Orc, and Parquet. So you're going to see probably 2 or 3 more of those get built into there soon. And yeah, I mean, it's hard for me to say exactly what every company is doing, just because I don't have like a great, pulse of all these different use cases. But I think a bunch of startups are starting to use it. Big companies are using it. People who are on cloud services generally seem to want that as like a first-class feature. You have S3 tables, which is basically a full new version of S3, except completely for Iceberg data. So it's a way to store your data cheaply and then use any engine. So it seems to have really kind of permeated the batch data community really quickly.
Yeah, it seems like it has. I was also trying to reconcile the real-time usage of Iceberg because, like you, I saw Moonlink when they came out. I've seen some Kafka companies or Kafka-focused Iceberg companies, and some of them compete under ingestion lag, meaning if a data point comes in Kafka, how many seconds, minutes until my Iceberg table can show it. And I'm kind of the impression that it's extremely niche for now. The desire, at least, to have like a real-time Iceberg, for lack of a definition, whatever, within minutes, being able to query the data. Like my understanding, which is completely uninformed, is that it's just there to like store data of some, OLAP stuff that you query once a day.
That definitely seems to be the general case. I know when I was at the summit, Google mentioned that they had a lot of people who wanted lower latency access to their Iceberg data. I guess the problem with real-time and low latency access to batch data is that in some senses it's kind of a code smell, right? Where it's like, well, if you need your data less than 5 minutes, maybe the right thing to do is not be putting it as files on object store, and maybe you should be using some sort of streaming pipeline. So
maybe not even columnar.
Yeah, honestly. So, I think depending on who you speak to, they might have different opinions on this. Some people are like, absolutely, yeah, this should go in Iceberg, and like this should be a first-class citizen. And I think others are like, well, there are systems like ClickHouse and Doris and Druid where, they have these in-memory buffers, and they're actually really good for low-latency SQL querying, but it's just less data because you're not going to distribute them as easily. And then there are people who are like, just go use a stream engine and pull your like Flink streaming job, or use Materialize or something like that.
Just to mention, there's also a difference between low latency and ingestion lag. So I was mostly referring to ingestion lag, or like how fast can I get my data to be reflected in Iceberg, whereas query latency can be, if it's there, how long does my dashboard take to load?
Sorry, yes, I was referring to, I was using them interchangeably, but in this case I meant low latency as ingestion lag. There are people who do low latency dashboards on Iceberg. That's where that company Firebolt, I think, is really trying to make their niche. But you're right, I should be specifying ingestion lag. Okay.
Yeah, so I think it's niche as well, and I'm not even sure if Iceberg should move into that direction. I mean, so Paimon is optimized in that direction, Hoodie, I think, I'm not even sure if Hoodie was optimized in that direction. It was more in the incremental updates.
Yeah, they claim to be a streaming format. They do similar LSM tree stuff. They have indexes over their data that can be used, I think, on the Upsert path. But their indexes are more like Bloom filter indexes and less like, I'm going to sort this data. So the Hoodie engine support, in my experience, also is not nearly as good as Iceberg's. It's a lot of Spark, but Iceberg just, at this point, pretty much every major data querying engine supports Iceberg, and it's just a really nice thing.
So, but it's been funny to see how you found your way into the streaming space. Going into the Iceberg space and then figuring out the deletes, which is again sort of almost a streaming problem, right? Because in theory, there's not too much downside to just the delete problem. If you have to retry and everything and not use IceStream, I guess you just did to be more optimal.
Yeah, I think ultimately that's where the community seems to be converging is one person has a feature that he's building out where Flink is going to keep a local index of the table. It'll be a distributed local index, but then it'll try and synchronously convert equality deletes to positional deletes before the data actually even reaches the table.
Right. So I guess the year's focus has been mostly table formats. Well, first I will ask you, do you have any other thoughts on table formats before I ask you about something else that we didn't cover?
It's a good question. Admittedly, no. I just think that there are a lot of people trying to do a lot of different things in them right now, and especially it feels like the review bandwidth is low. So I think I'm encountering like the normal open source problems that anyone else might be experiencing. And frankly, Iceberg is pretty good on that spectrum, all things considered. I looked to consider making a commit in Avro the other day, and I looked for about 30 seconds, and I was like, I'm not even going to bother. So, Iceberg is great. The community is really cool. Everyone's super responsive, and I think it's a great project. But there are just natural challenges associated with doing open source work.
Definitely. And are there any other sort of technologies you've been looking into or express interest in, aside from, let's say, table formats and maybe streaming engines?
Recently, no. That's where a lot of my focus has gone. I was a little bit curious about like vector indexes or retrieval augmented, whatever RAG stands for. Mm-hmm. Retrieval augmented, is it generation? I can't remember. But basically, I was a little interested about that just because that was kind of poking on another trend that I cared about, which was, can we put a vector database on object store? Now, fortunately, two people have beaten me to doing that. One is Turbo Puffer, and the other is Amazon, because Amazon started S3 vectors. So I was like, all right, I'm probably not going to pursue that. I was also interested in the kind of database on object store architecture. Neon got purchased by Databricks a couple of years ago for incomprehensible sum of money that I can't even think about. And I was looking into that just because one thing that Neon does is, if you run it on Amazon, for example, I imagine they must still be paying that cross-AZ egress traffic because you have a write-ahead log, and it is sending that write-ahead log entries to multiple availability zones because they have to be replicated to be safe. Okay. So I was wondering if there was any sort of arbitrage that you could use there. For example, Microsoft does not have cross-AZ replication costs, but what could you do on Amazon to try and mitigate those? I was like, oh, maybe I could use Kinesis to do this with a write-ahead log instead, because there are no AZ charges. Again, I don't really think it's worth my time or necessarily a good architecture to, just try and avoid these cross-AZ costs for like a very niche part of a very niche database. So that's ultimately why I'm kind of converging on focusing on stream processing. But I love to learn about all this distributed system stuff. I think it's very interesting. A friend of mine, was telling me about Temporal recently, so I looked into their docs very briefly. And anytime I get the chance to look into a new technology, I really love to do it.
The S3 as a file, as a storage system is really interesting, and it being a primitive in the new set of data infrastructure software that's coming out. I want to ask you what you think generally about this trend, and also you said that in your current company you're actually self-hosting on-premise. So for someone who's seen both worlds, I want to ask you, like, what do you think of on-premise, actually? What's your honest opinion on it? compared to the credit it gets on the streets?
Good question. Well, right now hardware is really expensive, which is unfortunate. I think otherwise everyone would be very cool with being on-prem. I think it makes me take less for granted the amount of work that it takes to run a system like Amazon S3, because, we see that as the client and just think, oh, this system's working at all times and nothing's ever going wrong. I mean, I can only imagine the capacity that they have to purchase and the amount of planning that they have to do at all times. And I think that also, Amazon does a phenomenal job of somehow like avoiding a noisy neighbor problem for the most part. Whereas, my company is always stepping on each other's toes with our shared resources. In theory, you're kind of sharing the same clusters as other people in S3, or at least to my knowledge. I don't, know their internal architecture so well, but it's pretty phenomenal that you can kind of operate like normal, even if someone else is just absolutely abusing their services. So I would say, the reason that we do on-prem is mainly just for cost savings reasons, but I think it gives me a newfound appreciation for the cloud providers and the amount of engineering work that has to go into like building these.
Have you seen the S3 blog posts? They've been very vocal about how it works in a way and how they fix the noisy neighbor problem. They were sharing that, well, first they They do erasure coding, so each piece of data basically gets split into many nodes, and then they shared the most interesting thing that's not extremely intuitive is that at a certain scale of multi-tenancy, the load actually becomes very predictable, and you can pretty much predict how much a single node is going to do depending on the pieces of data you put on it. Because they have this really cool gif of the thing where like the graph goes like this, like very spiky and unpredictable. But the moment they add more and more workloads on top, all these spikes sort of work like they interlap with each other, and it just becomes like a gradual thing.
So that's kind of hilarious. You're going to have to send me that article offline.
I will. It's mine, actually. I blogged about it. But, of course, they did it on Talks, at reInvent, and etc. It's a way longer format. But, yeah, well, I think we covered a lot for a single hour and 20.
I'd say so. My face is starting to go red from talking, so that's normally a good sign that we've, hopefully spout out some good information, or in my case, nothing too useful, but I just love to ramble. So I appreciate you giving me the opportunity to do so.
No, it's very useful. These details are not talked about barely. I'll be surprised if you can find many YouTube videos that talk about such details. I really appreciate it for coming on. Thank you so much. And I'm excited to see where your projects go, but in general, I'm excited to see where the channel goes as well, because one thing I find very cool about your videos is like they're very down to earth, and at the same time, they explain the concepts very clearly. Like there's no, like it's very straight. I watch a video and I immediately sort of learn, either how the thing works or what the problem is and how you solved it. So, great job on all the work you've done there.
I appreciate that, Stan. Same to you. Again, keep up the great work on LinkedIn. I'm looking forward to seeing all the posts, and thanks for continuing to educate me about streaming. I would not know a lot of the things that I know without you kind of getting the ball rolling for me, so I appreciate that.
So yeah, thanks for coming on. I'll see you around.
All right. Have a great day.